in the runtime stuff are the images doesn't show. No problem. So we have some here are Richard and Heidi Ronnie, who were the brains that developed all the first stuff about the runtime. So what did they do? They implemented a sheet. They started by writing a sheet in Smalltalk, and they say, "Wow, I have a sheet, and this is what usually is part of the VM. So what else can I write about the VM?" So they also did GC, and to do GC, they say, "Okay, but we have to talk about the meta information of the objects, like their size or their header." So they came up with this great idea, which are under primitives, of which I'm going to talk a bit later. And then I came. So we asked ourselves, what can we do to get rid of the VM? We are running on a digital derivative of Smalltalk, dialect Smalltalk. So we have a VM that does cheating, that compiles bytecodes, and then nativize just in time. I use the word nativize to talk about cheating. We have this VM that takes the bytecode and nativize them just in time. So what can we do to get rid of the VM? What else does the VM do besides the sheet and besides GC? So we said, okay, what's the first idea? How do we get out of the VM? How do we get some Smalltalk code running without the VM? We said, okay, first we have these little things that are, of course, with objects. We have these little things that are Smalltalk libraries in our Smalltalk. So we said we could use this to generate the usual libraries of Smalltalks that are like tiny image files, and we can say, okay, besides the Smalltalk code and the bytecodes of the methods, all that stuff, we can also add the native code, because we did a sheet in Smalltalk and we can control the native code generated. Okay, so we said, let's add this native code to the library. And we have a special library which is called the kernel, Smalltalk kernel, that contains everything that is needed to bootstrap the system, almost anything. Okay, if you have a VM, the Smalltalk kernel can bootstrap and load any other library. If you don't have, you should add something more. But we said, okay, start with objects. Just generate native code for all methods, and then let's see what happens. So we implemented this nice stuff, which is the native code, which is the way we store the machine instructions of this Smalltalk runtime. Each compile method points to a native code, but it's not the actual machine code, but it's an object that stores the code inside the byte array, and also the references that this code has. Because if we see the code as a byte array, we are going to see something like this. Okay, but if we disassemble this, we are going to see something like this. And then, maybe you don't see it because the font is tiny, but there are many references to memory there. Okay, inside the code. So, with the native code, we can abstract the idea that we have machine instructions with references. And this is very transparent to the whole runtime. So we put the native code and we got rid of the VM. Okay? Is it enough? Of course not. Of course not. There are a lot of things that we should add to this. And to understand what we have to add, I made a list. So what are the things that the host VM provides besides cheating and besides GC? So one of the first things are basic objects. When you look at the native code of the VM, the generated code of the cheat, you are going to see that, for example, true, false, nil are all place it inside the native code. So the sheet puts the direct address of the object. Also, we have to we have method lookup. Each time we send a message, the sheet places a call to the message lookup. Okay, we don't see it, but it's there. We also have primitives. When we write a method with a primitive, the compiler puts a special bytecode, prolog bytecode, that the nativizer nativize as a call to some special native machine instructions. And then we have something that we call native helpers, which is something that is not shown by the VM, but already also exists. Like when you implement a method that is an environment, this method is going to need to create this environment when it's run. So you have to create an array. And how you create an array? When? Well, all you have to do is send array new of some size. But in the code, you are going to see that it's a reference to the array class, and there is a send of new in the product of method. Okay. So, for example, when you write true in a method and you set this method, you are going to find a bytecode that pushes true into the stack. Okay? This push is going to get nativized as a load true, which means move EX the address of true. If you are sending a message, then there's going to be direct access to the method lookup. So, for example, when nativizing a message send, a bytecode that sends a message, you are going to do something like what is shown, that is to load the selector, and then you are going to jump to the method lookup of the virtual machine. Okay. There used to be also bit-to-bit compatibility with primitives, and when you wrote a method that used a primitive, the nativization of the product bytecode made the call a direct call to the primitive that implemented what you were wanting. And finally, these pieces of code that I mentioned, like sending new to array, are things that are placed in the VM, and the nativizer has to call, and their names are not accessible by the Smalltalk thesis. Okay, so all these things that are shown are things that should disappear if you want to make a Smalltalk that doesn't need a VM, right? So, for example, how can we connect method with lookup in a runtime that doesn't have a virtual machine? Well, we can implement lookup and invoke, okay? And what is lookup and invoke? Lookup and invoke means to fetch the selector, take the selector, look for the class that implements this selector, and then invoke the compile method found. Okay? And we can write this in Smalltalk. Here is the code, it's small, but I don't want you to look with much detail. But the thing is that as you are doing lookup, you can't let this method be executed just as it is, because this method sends messages. Okay? This method, for example, has to find the compile method, and it sends a message which is lookup for the symbol. And what's the problem? This will call a recursive lookup, and a recursive lookup, and a recursive lookup. So we implemented, because we have the sheet, so we can access the sheet, we made a lookup nativizer that let us to say, okay, but these are special messages. We are only sending them during lookup, and we exactly know which is the method that is going to be found. Okay, so we are going to tell this nativizer, the compile method nativizer, that when it finds this method, it should just involve the method that is going to be found. I mean, underscore lookup is only implemented in object and it's the only method that is going to be found. So we can tell the nativizer that instead of sending the message underscore lookup, just to invoke it. Well, under primitives are a great idea. Here we have the implementation of behavior method. You can think of behavior as something that is similar to the class, not exactly that, but if you see the object in memory, you are going to see the object preceded by a header, and this header usually points to a class, and in our implementation it points to the behavior. It points to the behavior in case the object is not tagged. So if the object is tagged, which means it's a small integer, we have to check the behavior. We have to take the behavior of the object of small integer class. But if not, we can just access memory, access the header, and there we are going to find the behavior of the object. So now, how is this implemented? The nativizer also has hooks, so that when we send underscore is small integer, this message is also not sent as usually, but it's actually in line with some lines of assembly. So we don't have a performance hit, and we can do fancy stuff like directly accessing the memory, and it lets us implement a lot of things. Like, for example, we can implement primitives. For example, we can implement, this is implementation of value in our Smalltalk, which is first checks that the block has the same amount of arguments that it should. Okay, if you send value, it should have no arguments. But then it has to find the native code of the block, and then it has to transfer control to that block. Okay, and transfer control 2 is another primitive, so that there's some inline assembly that is generated when cheating this machine code that jumps to the code of the block. With this under primitives, we can implement any primitive. And if we can't, we can add another under primitive. Okay, so let's think, for example, how we can implement object new in our system. Well, if we are going to create objects, we are going to need an arena, a place where to store the objects. When we generate the library, we have an initial arena that knows where the memory starts of this arena, where it ends, and what is the free space. Okay, it has pointers to this free space. And we can then generate a small library that has only a few free space, so that the file of the kernel doesn't occupy much size. And after initialization, we can create a new big arena that occupies much more memory, so that we don't have to care anymore. But this is how it works. And what is implementation then? We have this implementation of primitive new. I mean, when you send new in our bootstrap system, we are going to execute what is in the hosted VM primitive new. We have to make some replacement of the names. We can't directly replace the new methods in object, in species, or class, or whatever you have where you have it. We can't replace it, because if we replace new, the system just hangs. Okay, so we have to give it another name and then replace. When we are bootstrapping, generating the library, we have to put the name new. The thing is, it looks nice because everything is solved with message sense. And many of the things that the primitive does are already written, because, for example, here we are taking the size of the index of an object to create a new one. And in size is a method that was already in the kernel and was already implemented. We don't have to implement things twice in this runtime because there's no other, there's no C code or something like that. You can just reuse the code of the kernel. There we see below that we are just allocating this allocation is going to be asked to the arena, and the arena is going to give us some raw space, memory space. We have to initialize, and then we are free to give the object to whoever asks us. So there are many primitives, but well, there aren't so much. Like I don't know, maybe 50 that are necessary. We implemented all of them to have a working kernel. We implemented things like add, put, or things like perform, value. But we also implemented things that were really real fun. Well, all of them were real fun because we had to find a way. But for example, things like become was really interesting to implement in Smalltalk because you are dealing with your objects and it looks really cool, the code. So it was really nice. And all these things we put them in the kernel we are generating with the kernel builder. So we had to do some fancy stuff, like for example adding future Smalltalk, which is the global Smalltalk that is going to be added to the library. Okay, it's not the same that is in the host VM. We have to add another. We have to add to this library true, false, nil, and many big classes. And after all of that, we just write the library, and it's not there, but we are going to set an entry point to the library. So to some native code of this library, so that when the operating system calls us, we are going to execute some bootstrapping and initializing method. And well, but we have to generate an exe file, and this was already done for the sheet. After the sheet was done, the next thing was a PA file generator, so that they could put the sheet in a DLL, and also did the same with the GC. And we also did the same with libraries. So now our libraries can be actual DLL files that have all the concepts. So we applied some magic to this library that we are building, some more magic, and then we have this Smalltalk library made an exe. Okay, so you can execute that, and it's really cool. Now I'm going to talk about something that we already presented some of this work in the Smalltalk last year, in the Smalltalks in Argentina, and we made some advancements in what I showed before, and also things that I'm going to show now. For example, being minimal, which means we are making a system that doesn't need, I mean, it can use HEC and will be happy to use HEC, but it doesn't need it. So if we want, we can load it. We could load it. We don't have the HEC just yet. But it also doesn't have in the kernel the compiler nor the native ISO. Okay? So this is a bit strange for Smalltalk, but I think that making a minimal kernel is good because it will allow us to do some fancy stuff that is not possible today. So the way it works, for example, suppose you want to make an application, you can take all the code of your application. If it uses just the code of the kernel, you can generate this application with our DLL builder, so that the kernel will load it. You can tell the kernel load this library and execute it. So your program is going to be like an exe file, which is lib, and also your library, which is a binary file. Okay, that's one possibility. You can also build a standard library without native code. This native code is going to need the JIT. Okay, so when you need the JIT, you can load it and use this JIT, which is its native code. The JIT will always have its native code because it wouldn't be able to nativize it, no? And so you're going to generate the native code on demand for your library. You can also work without a compiler. I mean, if you make a library and you don't want to write new code, then you can work without a compiler, and if you need a compiler, you can load it so that you can work with new code. And also this compiler, for example, now we are shipping it without native code, because of course we can load the JIT and nativize the compiler on demand so that we can write our code and compile this code when we need it. And also this is fun because we are loading the compiler to compile some code, but then we want to execute the code, so we are also going to need to load the nativizer. But actually, we are going to load the nativizer to run the compiler code, and then we are going to run the nativizer again to nativize the compiled code of the method route. So it's like, I don't know, it's a dependency chain that is interesting. Now we are going to do a demo. I'm going to start showing you